designer about data schedules type.
Thank you. Good afternoon. My name is Ido. I'm going to tell you about Mergeable Summaries today. My co-presenter is not here, is Justin Taylor. And this is shared work with a few of our colleagues, Lee Rhodes, Kevin Lang, John, I forget the last names, I apologize. Let me, I'll get all of them. Alex and John, they'll kill me for forgetting the last names. This work came out of practical needs about summarizing and working with large data, and ended up being a very interesting fertile ground for actual research. So I'll brief through really streaming and the need for mergeable summaries in big data, and then we'll kind of dive into kind of just see some of the theoretical results and some of the practical applications. So this is a merge of those two things. So in standard data mining, or kind of the old school thoughts of how we do data analysis, we just collect data on some disk, and then we compute, kind of load in the memory and compute on it. And then we started thinking about data as being too large, and we collect it on a bunch of disks, and we then still have to compute it in memory. Then we think about things like MapReduce or other scatter-gather approaches, where we load the data on a bunch of machines, and we kind of send the executables or the code to the data, and we have some form of interaction. You can think about search as being, or databases as being kind of like that as well, where the data is more static and the execution goes and kind of is a part of the communication. But if I don't need to sell you on the idea of the explosion of data, and so this is like a meta infographic on big data. So this is an explosion of infographics about big data, and so we have this is already. We can't even store the infographics about big data anymore. And as the head of Amazon AI Labs, we work with a lot of the Amazon Cloud services like SageMaker, which is the new machine learning platform, Kinesis, so it's our streaming solution, QuickSight is a BI and analytics platform, and so on. All of those deal with terabytes and petabytes of data, and they need to be very interactive, and at the same time very efficient and quick. And so we have to work in a much more efficient way. The streaming model is an incredibly efficient method by which you funnel all your data into something that creates a summary of your data, which creates something that we call a sketch from this point on. And that sketch gives you a good approximation to whatever it is that you are trying to compute, whether it's some statistic or some property of the data. And with mergeable summaries, which is kind of the focus of this entire talk, is an even more restricted setting where the data is not even collected in one machine. Actually, you have a lot of machines collecting separate parts of the data. So the data is sharded in some way that is unknown to you and completely arbitrary. Each machine computes a small summary, and only those summaries are shared with some global sketch that just merges those different data structures and needs to be accurate and faithfully represent the data, like the global data. Right? So there is no assumption on stochasticity. There is no assumption on how the data is sharded. The data is sharded in some completely arbitrary way. And you can think about those as maybe machines collecting some user actions from all over the world, and you can't assume that your users in Europe behave the same as your users in South America. Okay, but you still want to have some global behavior. So why is this so important? So if you think about big data and computing things like number of unique users who visited all my websites all over the world. Okay, think about Amazon.com, maybe really caring about something like that. Okay, the way you would think to do this is I'll take my data, I will shuffle it to other machines to do a join. So I will kind of share them by key or by user ID somehow. these machines would uniquify the keys, will count how many unique keys they see. They just have the sum and then send the sum to some central machine. But this thing here is a shuffle. You're actually broadcasting all the data from one set of machines to the other. Okay? So this might move anywhere from gigabytes to terabytes of data, and that could take hours and cost you hundreds of dollars. If you do this with sketches, each machine would only sketch its local data. It sends only the sketch, which could be kilobytes, and this thing is going to be merged in a matter of milliseconds, and this entire thing will be done. Okay, and so this thing actually takes. Go on.
What is sketch?
So sketch I'll go into how we actually sketch. What does that do? Okay, think about this some compactor, something that creates some very concise summary of the data, and depending on what it is that you want to summarize, it does something else. Okay, so I'll give you a very long list of what those things could be. Go on.
And in terms of framing, could you look back a few slides to the overview? Yeah, that one.
This one.
What's sort of the temporal relationship? I assume queries are kind of asynchronous, and the merge sketch results are continuous in some sense.
Right. So for all of this talk, I'm gonna assume data just keeps on coming all the time. So think about this: visitors to websites or some machines in some factory spewing out some sensor measurements or whatever. There's going to be some ongoing stream of data that might be collected by, I don't know, hundreds or thousands of different sensors or machines.
So can I think kind of those results on the top as being kind of a dashboard-ish kind of?
Yeah, so this thing, you might actually push this thing to some front-end thing, and you might want to refresh this every few seconds or whatever, or however, whenever somebody actually wants to look at it or something, yeah. Where does this idea also come up? If we look at just data mining or taking statistics or doing all sorts of analysis, if you have this data coming over some period of time, the standard thing is to do windowing. So I take 3, 4, 5, 10 days. So okay, that maybe goes far enough into the past. I will create some process whereby I'll take those, like say 3 days. I do some, crunching, and I'll create some model or some measurement that I care about. But in this way, I actually have to process every piece of data 3 times, and my models only contain 3 days worth of data. Whereas if I can do this collection and merging, I can actually sketch things only once and then just merge with the day prior. So each data is processed only once, and my models or my statistics are actually valid for all of history. So it's a double win. The same thing is true for dynamic windowing of queries along these lines. If I have some binary merging tree, then if I want to know some statistic about some sequence into the past, I can now just take these 3 nodes of the tree and just merge those sketches, and I would get exactly the range that I care about, and I don't have to go and do the merges for everything. And if you know what OLAP is, it's kind of, I forget the online analysis, I forget the name, the P. But it's a common thing, so you'd have a set of events, and you might want to care about some select operation. So you want to know, this is a map of Westeros. So you might care about how many, I have some events that I want to know the latency of. You want to say, maybe I want to know the latency of events in all of Westeros, or maybe I want to know in just, I think it's the north in like the first quarter. So I might have a sketch or one of those data structure for each territory for each month. And to get the quarter, I just merge 3 of those, and to get the entire region, I just merge the category. And that's a very common use case. So I just save a small amount of data, and I still get a lot of query combinations that are possible. So I'm not going to go into the hardness results of what's possible, what's impossible, but a lot of things are impossible in this model. It's very easy to show that, for example, if you want to compute the exact median of a bunch of numbers, it's impossible. And I'm not going to go into why, but you can convince yourself that that's impossible. But if you're willing to get even a small amount of approximation, and in most of those cases, you don't mind getting a tiny amount of error or approximation, then we actually have very good algorithms to do a lot of different things, from counting distinct elements and estimating entropy of streams, and of course, all sorts of samplings. For matrices, you can do low-rank approximation, specification. For vectors, we can do clustering and linear regression and all sorts of machine learning and density estimations. We have some results for graphs. This is kind of semi-streaming, so the space is proportional to the number of nodes usually in the graph and not the number of edges, which is polynomial, so it's called semi-streaming usually, but still. So in this talk, I'm going to tell you about an open source library that we've been writing for several years, and these are my colleagues. So I'm just going to do them justice now. So it's Lee Rhodes, the chief architect of this thing, Kevin Lang, who's been the lead scientist on this project for a long time and has been working on it for several years. Alex Saidakov is a lead engineer on this project also for a long time. Justin Thaler is my co-presenter who's not here, professor was in Georgetown. This is myself, John Malkin, also a scientist and engineer working on this project for several years. We've just hit the 500 stars on GitHub. I don't know if you know what that means, but for those of you who do, we enjoyed that. Okay. This library that I'm going to show you is actually used in Yahoo, and Splice, and Druid, and Amazon, in many other companies. It's production ready, and not only is it production ready, it actually contains a lot of the very new research that we have on these topics. Some of those, the latest publication is still in submission. We have papers in Fox, in internet measurement conferences, in NIPS and other places. So this is so this is one of those rare occasions where cutting-edge technology and code actually meets cutting-edge science. So in this talk, I'm going to just cover quickly counting distinct elements, item frequencies, and approximate quantiles. All of those problems have been studied carefully and by many others before us. When we approach these problems, we really care about writing great algorithms that work in production. So it's about simplicity of the code, provable correctness, because those are going to be used in the wild where we don't know where they're used. And in the same time, actual efficiency. So we don't, for us, we truly very much care about the constants. Okay, so it's all, big O notation is not exactly where it's at often, as you well know. How much time do I have? I don't have.
2:40.
What?
Until 2:40. That includes time for questions.
Okay, I have plenty of time. Excellent. All right. So counting distinct elements. This goes back to the seminal paper by Alon Matias and Segedi, and there's been a long list of authors of papers on this topic, including some people in this crowd. The work by Kevin, Lee, and Justin took a set of these results and unified them into this general framework by which you take items, you hash them to some value between 0 and 1, and you keep everything that falls beneath some value theta. Okay? And from the value if you do this carefully, from the value of theta and the number of elements that you have that map to the value lower than theta, you can get the statistics that you care about. And they show that a very large number of, several algorithms actually map just to different mechanisms by which you decrease theta with time. Of course, if theta is 1/2 all the time, you'll end up sampling a lot of things and you'll run out of memory, so you have to make theta smaller with time. Okay. They give new variance bounds. And of course, there's a very careful implementation of these algorithms. And what what we see is that if we do this carefully, then we take things like adaptive sampling and KMV, which are both instances of this theta family of theta algorithms. And if you compare them to an algorithm they called alpha algorithm, I'm not sure why, but then practically it just outperforms both in update time and in evaluation time pretty consistently. So there isn't this like jagged behavior of adaptive sampling, and it just consistently outperforms KMV. Okay, I'm not going to go into, so here I want to show you, actually want to switch to a live demo for a second. I know this is a theory crowd, so this is not common, but I'll do it anyway. If you want, you can, if you have a Mac, you can just brew install sketches. That's those two lines. You might have to install Homebrew before that, which is kind of the package manager for Macs. But let me show you something for a second. Oh. I want to see my screen. Okay. Can you see that? All right. So, I think this, where am I? Interesting. All right. Okay, so I have this file that just contains numbers. The number in place I is a uniform number. It's like a uniform integer between 0 and I. You can convince yourself that the expectation of number of uniques is n over 2 if you do that. It's a nice exercise. So if you wanted, if I just give you this file of numbers and I tell you with the duplicates, I want you to just tell me how many unique numbers there are here. So the standard way to do this in Python, who does sorry, in Unix, who's a Unix pipes guy? So how do you uniquify things in what? You can do unique, but then you have to sort first. If you just do unique, that's just gonna, so you have to sort.
You can like sort dash U, right?
What?
There's a flag for sort there's a flag for one of them that will make it do both together.
Right, exactly. So if you do this, unique, and then just count the lines. Okay, so this would hang, or just, oh, what?
Word count as the flag, right?
Oh, yeah. Of course, this will not work. So you're right. I can just ask sort to uniquify to begin with. That's not going to work. I mean, that's going to take forever too. But it turns out that sort spends most of its time string comparing between the, so these are strings. It doesn't know its numbers because it's a file. It just thinks so, comparing lines. So I can tell sort that these are actually numbers, okay? And that thing will work. It will take some time, but it'll work.
How big is n?
What? N just tells it to parse the lines as numbers.
How big is the data?
Oh, okay, that's a good question. So this is 5 million things. If I just do this, it's 10 million. Okay, and you can see also that I/O is not the point. So I just piped it into comp, so it was pretty quick. So you saw how long sort took, and it actually had to load the entire thing into memory. That's roughly 74 megabytes, and that's what's happening. So if you try to do this with data sketches, it would look like that. Oops. I apologize. We just changed the commands. Oh, theta. Sorry. All right. So that's it, and it tells you it's approximated as 4.9 million, and it's between 4.8 and 5.1, and you can change the accuracy and so on. But the interesting thing is that this thing, not only did it finish in like a tenth of the time, it actually only used like a few kilobytes of memory instead of 74 megabytes. If you do it once on a laptop, that's nice, but it's not a huge difference. If you try to do a 100 million of those on a server, this would be possible and something else would just explode or just will never finish. So, what? So it's 1 over square root the size of the sketch, roughly. So I can change the size of the sketch. I can set k to be larger.
I mean, this example?
Yeah, so now this is way more accurate. So this is saving like 200K, 20K, 200K items, okay, instead of 5 million.
So this is using the adaptive theta technique?
Yeah, so you can decide how much memory you're going to use. The more memory you use, the more accurate the sketch is. Yeah.
Were those type bounds, or are they like a confidence interval?
Good. I forget. I think it's 95. I have to get back to you on that one. I don't remember. I think it's 95. Okay. So this was just my. That was just a live example of why we care about these things. So this was. So another problem I'm going to introduce is item frequencies. So again, a long list of authors starting from, actually I think the most significant paper on this is not here. Aha, here it is. All right. Well, one of your many people in this room's colleague, Mr. Professor Grease. A paper from the 80s on how to approximate frequencies or number of counts of items in a stream. When we started with this problem, we noticed that most of our customers are actually asking for weighted updates. So they would say, okay, we don't add 1 to counters of items. We actually have weights. So think about this as like number of cycles spent on some process, or time spent by some user on some application, or so on. So the problem is defined by I have updates of item IDs with some weight, and I want to be able to approximate the weight of every item up to some epsilon error, and it's epsilon times the total weight of the entire stream. Okay. When we took on this problem, we managed to actually improve both the worst case update time, improve the merging procedure. So now merging is significantly faster and more, actually also simpler. We improved the estimator. So there are 2 algorithms. So Mishra agrees, also called frequent items, has one type of estimator, and another paper called, another algorithm called space saving has a different kind of estimator. We actually showed that if a hybrid between them, it tends to be more accurate. This is a practical observation. Both of them provably are somehow the same. And of course, with a very careful implementation of the algorithm itself. So let me just tell you about the idea there. And the idea is very simple, and it's very similar to both frequent items and space saving. It's just, if you don't know it, I think it's a cute algorithm. It's worth seeing. I just keep a bunch of counts of items, and the total weight. When I get a new item that I need to aggregate the weight for, I just add it to the sum. And then I get maybe a new item that I don't have a counter for. I create a counter for it with the appropriate weight. But then I ran out of space. So what I do is I take roughly the median weight that I have in my data structure, and I just chop everything by that amount. Okay. Okay. And which, of course, if you take out the median, then roughly half the items are gone, and you have space to insert more things. Okay. And the interesting thing is, that finding the median can be done. Finding an approximate median can be done very efficiently. So I don't even need this to be like an exact median. I can just have an approximate median of the value and just chop everything by that amount. So if you just sample or take any way of approximating the median, we see that the error is actually not much worse than what happens if you take the smallest item, or if you try to do the most careful thing possible. And in fact, you can make the errors be completely the same if you just make this sketch slightly bigger. Okay. But the update times are significantly faster. So these are the update times of other algorithms, and this is the update time of this algorithm that I just showed you. Yeah.
The item, that's an exact match. It's not a bin. There's no binning going on.
No, there's no binning. It's an exact match on the ID, and then counting. Yeah. So you can think about, so for this problem, we actually investigated. So I'm showing you just kind of the bottom line, all the results on count sketches and count mean sketches and all sorts of bucketing and hashing tricks and so on, just end up being significantly less accurate. Yeah, I mean, it's too much to discuss. But there's been, took us a long time to evaluate that this is actually, in our opinion, the winning strategy. Okay. The surprising thing is, just as a curiosity, I'll tell you in a second how this is used, but just as a curiosity, the interesting thing one of the hardest things to do here was to figure out, so here you have a hash table with like L objects in it, and you need to delete half the items in it. So if you've worked on data structures, you might think to yourself, oh, deleting things from a hash table is O of 1, who cares? But it's the big O thing. So if try to think of a hash table that optimizes the operation of deleting an arbitrary subset of half the keys, and you'll see it's not an easy problem. I specifically optimized that for almost a month, and I had to go back to like literature from the 70s. So just an example on how this is used. If you look at, I forgot that I'm not in presentation mode. Okay, good. So if you look at mail that Yahoo Mail gets, and these are old slides from some work, you can try to see that so getting an email from so if you get an email from Payless saying you have some order confirmation, getting another email from them saying that you have an order shipped. Now, maybe you can think about this as any shopping or any other interaction that you have with the world through emails or with some servers. You can figure out that the probability that you get this email, given that you've gotten this one before, is significantly higher than just getting this one independently. So to do this, you have to look at every pair of types of emails and figure out what's the relative lift in probability. And that's a squared problem that's impossible. But if you use these sketches, you can just add like 1 over the ground probability for each element, for each email to seeing the subsequent element. This problem goes down from being O of n squared to being O of n. This goes from being impossible to being possible. So this is, so you can think of sketches taking O of n to O of 1, which is taking something hard to being something easy. But in systems, oftentimes you have many of those. So it takes something like O of n squared to O of n, which makes something impossible to something hard. And by the way, if you do this, you start seeing a lot of interesting patterns. So of course, order confirmations move to shipping, and things like reminders to pay bills end up with people canceling stuff. Okay, streaming quantiles. I'm almost out of time, but in streaming quantiles, we have 2 papers on this. So this was, so let me define the problem first. You get a bunch of items. Just think about them as numbers for now, but they can be anything that's comparable, anything that's, and it's like full ordering on things. And a rank of an item is just the number of items in the stream which are smaller than it. So this would be like 0.6 times n is the rank of this color. Okay, and you need to process a stream and be able to produce an oracle that can compute R prime, which computes all the ranks for every possible thing up to sub epsilon n arrow. So it's approximating the quantile or the rank of every possible thing. Again, a long list of work that, we did not invent this problem. You can uniformly sample things. And then there's a sequence of results. And so maybe surprisingly, this result was actually before, chronologically before this one. But Feldberg and Ostrovsky had a result on show how, uniform sampling gets you a solution 1 over epsilon square. You want to do better than that. You can get 1 over epsilon, log 1 over epsilon of epsilon, which was thought to be optimal by most of the people that I talked to. It was not mergeable, and it was by no means a simple algorithm. And there is a paper that introduces mergeable summaries by Agarwal, Kormod, Huang, Philip, Wei, and Yi that gives a log to the 3/2 1 over epsilon solution, which we implemented in the library. But that didn't seem correct to me. I don't know. Logs to the 3/2 didn't seem like the right thing. I felt like something must be off. And so Zohar, Karnin, Kevin, Lang, and myself worked on it. And we figured that you can actually get a square root log 1 over epsilon solution, but that is both simple and mergeable. And in fact, you can get a, oh, I apologize, this is not an X. So you can get a log square log 1 over epsilon and get mergeable. So this should be a V, this is a mistake, okay? And you can get a log 1 over epsilon solution, but that's neither simple nor mergeable. And we proved that this is optimal space-wise, okay? So you can get space optimality but lose mergeability, or you can have mergeability and have something slightly less than space optimal. If you want to try to get both, this is still open. This is a great research problem. And I have a couple of minutes. I'm going to show you roughly how this works. I think it's interesting. Maybe show you some results, and I'll conclude with that. So, so let's define this buffer. So how these like quantiles things work. I'll have a buffer. This buffer is size k. So I'm going to store k items in my buffer from the stream. Once the buffer is full, I'm going to halt for a second. I'm going to sort these things, and then I'm going to delete half the items, either the odds or the evens. And then the items that I didn't delete, I'll output in double the weight. Okay, so what does that look like? Think about this as like some kind of adaptive sampling, right? If I choose to keep the even ones, then if for this value, so think about this is now not the stream, this is the x-axis. Okay, so these are the numbers sorted. So if I ask how many items are smaller than this query, then it's 2 every time. So this item is weight 2. Right? So I actually didn't change the rank at all. So this thing didn't suffer any approximation, any error. But if my rank was odd, then either I merge the 7 to the 5 or the 5 to the 7, in which case the rank has changed by 1. So every time I do this merge, I only suffer an error of 1, even though I've deleted half the items. Okay? So, so if you process the entire stream this way, you've taken k items every time, so the stream is of length n, so you've done this n over k times. Okay? And so the error that you introduced between this stream and that stream is at most n over k. You still have a stream of half the size, so you still have to do something with it. But that's easy. You just pipe it into another gadget like that. Okay, and just keep piping it to more and more gadgets until the stream is short enough to fit into one of them. So you just need log n of those buffers to fit the entire stream into it. And the error just multiplies. So we had n over k, now we have n log n over k. And if you set k to be log n over epsilon, then you get what you wanted, and the total space complexity is log square n over epsilon. This is a sketch called MRL. This is, again, from the 80s, or maybe 90s, I think 80s. There is a famous paper by Grindwald and Kahana that shows how to do this deterministically in log n over epsilon. So they removed one log n term but I'm not going to explain how that works. It's a bit of a complicated algorithm. But what Agarwal, Komod, Huang, Philip, Wen, Yi showed is that you can replace some of the buffers with sampling, and you can do instead of deleting either the odds or the even, you can do this randomly, and you get you get this result that I showed you, that I told you about, that log to the 3 halves. And what we showed later is that, in fact, you can make the first buffers smaller and somehow not hurt the performance or the approximation at all. And that removes one of the log n factors. So you have sampling, and then buffers that become bigger, bigger, and bigger until the size k. And the interesting thing is this sampling and these buffers kind of look alike. So you can think about this as this adaptive sampling. Instead of switching between sampling and sketching, it kind of slowly moves from sampling to something that looks a little bit more like sketching, a little bit more like sketching, and so on. And then you can replace the top buffers with this GK sketch and get the optimal thing. Which I really flew through this thing, but I think it's potential. I mean, I hope you got at least something out of it. But the interesting thing is that if you take this sketch that I showed you and tune the Ks such that it aligns with what you'd expect from the previous best result. So this is the error. I mean, it's different Ks, but they kind of match on the error. The size of the sketches that you get are significantly smaller. So these are significantly more compact in practice. And in fact, we have a follow-up paper that gives a bunch of a new set of tricks that improve the constants even further. So this is the better algorithm that I showed you a second ago is the orange one, and we managed to actually improve it even more. So in this talk, I only showed you 3 things, the top 3 ones. We have solutions for some of the others. Some of the things on this list are not implemented. Many other problems are open, and especially things with regression, with machine learning, anything that has to do with densities, and of course things that are touch on the deep learning and gradient descent and all sorts of stuff like that are wide open. So there is pretty much any streaming algorithm that you think about, try to think about in the mergeable setting. Try to think about how I can see my data in different machines and take only the sketches and merge them. And if you can do this in a provable way, let us know, and we'd love to really figure out how to actually get it into this library. That's it.
More questions?
What are the next main open problems with this thing we should solve in this context?
So yeah, it's interesting. So surprisingly, so clustering is something we're working on. It's still open, but potentially doable. I think problems in machine learning, in proper machine learning, are going to be very, very hard. Again, those are things we want to work on, but there are, maybe it's things that you guys can invest in. I mean, we just don't have the bandwidth to get to them yet. But things, even simple things like logistic regression, not to talk about deep learning and all sorts of stuff like that. This is like beyond the horizon. But yeah, I mean, that'd be very interesting.
What do you find is most in demand? What are you asking?
So unique counts is actually, like, just counting unique items is very needed, and just because the alternative is so painful and awful. It's like you really have these like huge joins and huge database operations to do something that, if you are willing to get like a 0.1% error it will be done in an instant, right? And the vast majority of people don't care about that. I mean, for dashboarding especially, they create some chart, and they just look at it, Really, I mean, if there was a 1% there, you wouldn't even, I mean, the width of the line is...
So I don't know if it's too detailed of a question, but what are the typical applications of heavy hitters?
Good. So heavy hitters does, so it's...
Or frequency estimation?
Yeah. So it's time spent either by users or by machines. Anything that has to do with budgeting, like cycles, or so people. I mean, so in factories and in IoT systems and so on, and you want to have a data. You have a compute center, and you want to know, give me the distribution of cycles per process, name of process. Okay, so now you have, I don't know, how many processors there, and you definitely don't want to have all of them save logs and funnel data in and out and do aggregations. That alone would kill you, right? Especially if you want to have some ongoing thing. If you want to see that some process starts going renegade and start like growing, this is super heavy if you want to do this. So the interesting thing, by the way, to note is that a ton of the literature in streaming algorithms is dedicated to turnstile and insertion deletion and so on. Some is dedicated to mergeability, but not nearly as much. We see in practice that people don't necessarily care about deleting stuff. They much more care about things being mergeable than about being able to add and delete items. And those tend to conflict, by the way, algorithmically. I mean, if one works, then if you have a linear sketch, anything works, but linear sketches tend to not be optimal for them.
Okay, that's then the speaker again.